Okay, so we are on the last question, question 6, which is on module 3, which is chemistry of the elements, right? So this particular question is about transition metals, and they're asking us to list 4 properties of transition metals. So I'm just going to go ahead and write those out here. 4 properties of transition metals. 1 is that they form compounds with different oxidation states. And something that goes along with that is the fact that transition elements and their compounds are often good catalysts. And that has to do with their variable oxidation states that they can possess. They have very high density. So let's write that one. They have very high density. And of course, we have to mention the fact that the transition element ions form colored compounds, right? The transition metal ions form colored compounds. All right, so those are 4 properties of transition metals. They form compounds with different oxidation states. Transition elements and their compounds are often good catalysts that's associated with their variable oxidation states. They have very high densities, and the transition metal ions are capable of forming colored compounds, okay? So that's our 4 marks. We're done with that one. So let's clear that and go down. Okay, and this question here is asking us about titanium 3 chloride. So that's a chloride of a transition metal ion, right? And that forms a violet solution when it's dissolved in water, right? So they're asking us to write the electronic configuration using the s, p, and d orbitals of the titanium ion. Now, we have to always be sure as to what they're asking us for, right? Is it the configuration of the atom itself, or is it for the ion? And in this case, they're asking us for the ions electronic configuration, right? So titanium, let's see. So titanium forms a 3+ ion as evidenced by here, right? So it would be TiCl3, right? And in that, the oxidation state of the titanium is +3, right? So this is the case where it has lost 3 electrons. It's 3 valence electrons. So loss of 3 valence electrons, right? Loss of 3 E's, right? And so if we're supposed to write the configuration, then it would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1, right? So that's what it would be for the Ti3+ ion, okay? So that's just this one, Ti3+ ion, right? All right, so that's our SPD notation of the electronic configuration. And so next they're asking us to explain the color of the aqueous solution. So they're saying that when we have this chloride, so when we have TiCl3 in aqueous solution, right? So in water, that's when we see this color, a violet color, right? So that's what they're telling us in the question here, that we see the color violet in that case. right? When it's in aqueous solution, that's what we see. And the reason why we see that, so let me get a text box to write that. So the titanium ion complexes with the water ligand, right? So that's the very first thing that's happening there, right? So the titanium ion is gonna then complex with the water ligand that's there. And then as a result of that, because the titanium ion has partially filled d orbitals, right? Remember, we only had one electron in the orbital here, so that's a partially filled d orbital. Then there will be room for an electron to be promoted from a lower energy d orbital to a higher level d orbital. The energy absorbed for this transition is equivalent to that of green light, and so we see its complement, which is violet, right? And so in a nutshell, that's really what's happening here, is that the titanium has a partially filled d orbital. So there will be room for an electron to be promoted from a lower energy d orbital to a high level energy, to a higher energy level, right? So let's write that. The higher energy level d orbital. The energy absorbed for this transition from that low level to the high level is equivalent to that of green light in terms of its frequency and wavelength, right? And so we see its complement, which is violet. So that's how we end up seeing that violet color. So it absorbs green and it transmits a mixture of the other colors. And so we'll see that as violet, right? And really what it boils down to, all of this, is that when the ligand, which is water, right, comes in contact with the titanium ion, it splits the 5d orbitals into two energy levels, where we have 3 down here and 2 up top. And of course, remember, we had only one electron in our d orbital from up here. That's what titanium ion has. It's a single electron in all of its d orbitals. And so there's a lot of room for this electron to be promoted, right? So once the ligand comes in contact with the titanium ion, right, then there's going to be that splitting of the d orbitals into two energy levels, where we have 3 on a lower level and 2 on a higher level. And so if this electron then gets promoted, let me use a different color for that, then gets promoted up to this level, there's an energy or a delta E, an energy change that's associated with that, right? Because this is a fixed quanta of energy that it's required to go from down here to up here. And so that delta E will be equal to H times frequency. And that frequency ends up being in the green region. So that's for the green light. And so we see the complement. So we see violet, right? Because remember, we're not going to see the color that we absorb. We see what's transmitted. And so that's how we see violet. Okay. All right, so that's what it is. It's really just the ligand splitting the d orbitals, and then we can have that electronic transition is what's at play here. Okay, so let's clear this and move down to this part C, where they're asking us, describe what would be observed when concentrated HCl is slowly added to an aqueous solution of cobalt 2+, right? So we have an aqueous solution of cobalt 2+, and we're gonna gradually add some concentrated HCl to it, right? So what we would see, what would be observed, they're asking us, so what would we visually see, right? And what we would visually see is a color change. Color change from, we're going to see a color change from pink to blue, right? From pink to blue. So that's all they want us to say for that part for 1 mark. We're going to see a color change from pink to blue. That's what we will observe once we're gradually adding in that hydrochloric acid. And they're asking us now, write an ionic equation to represent the observation that we see in C part I. All right, so they want us to describe this color change pretty much by way of an ionic equation. And that ionic equation will then be this one here. So that's going to be where we have our cobalt in aqueous solution. So that would be with this water ligand here. So when it's in aqueous solution, this is what we have. Let me erase this. Okay, so we're gonna have H2O when it's in aqueous solution again. So this is our original state where we're in aqueous solution, and we have our CO2+ that's complex with that water ligand, right? So this represents our aqueous solution. Let me this outside of that square bracket because it's the overall charge of the whole thing, right? So that's that. And of course, that originally is going to be pink in color, right? That complex ion is going to be pink, right? And then now, once we're gradually adding our chloride ions from the hydrochloric acid, concentrated HCl, what we're going to find is that this ligand is going to exchange with the water ligand, right? And we're going to end up getting CO, Cl, 2 minus aqueous, right? Plus that 6 water ligands that got displaced, right? So that's what we're gonna, that's how we can describe that color change using an equation. And so let's balance everything. So we put a 4 before this, and I think we're all balanced otherwise. And let's just write what color is associated with what. So this one, this cobalt chloride complex that gets formed as a result of that ligand exchange is gonna be blue. Okay. So this is how we would write that ionic equation to observe that color change that we see, to represent the color change that we would have observed in C part I, which is a color change from pink to blue upon the addition of hydrochloric acid to our aqueous cobalt, okay? So that's what we need to write there for those 2 marks. So let's clear this and go down. And down here, they're asking us to use the concept of stability constant, right? To explain the changes that we observe in C part I. So those changes were what? Let's go back, let's undo and go back up a little bit there. So the changes that we saw was that the chloride ion was able to come in and exchange with this water ligand to give us this cobalt chloride in the end, and then this free ligand here, right? And the color change was from pink to blue. So let's talk about that using the stability constant. Why was that happened, right? So first of all, we have to just state up front what the stability constant is. So let's talk about that, right? The stability constant is basically a measure. So let's write that. Stability constant is a measure of the stability of the complex form, right? So if we have a higher stability constant, it means that the associated complex is more stable and so much more likely to be formed, right? So let's bring it back to the question now. So in the above case, C part 2, the stability constant of the cobalt 2 right complex is much higher than that of the what we had initially. And so the Cl minus ligand was able to exchange all the water ligands to form cobalt. Okay, so let's tie this up nicely now. So this is what we're saying. We're saying that the stability constant is a measure of the stability of the complex formed, right? So if we have a higher stability constant, it means that the associated complex, right, that's associated with that particular high stability constant is going to be more stable and so much more likely to be formed, right? In the above case, in C part I, which is what we're talking about in this question, the stability constant of the cobalt 2 chloride complex is much higher than that of the cobalt hexaqua complex, right? So that's what we had initially in the aqueous solution. We had a cobalt hexaqua complex. So because the stability constant of a cobalt 2 chloride complex is much higher than that, the chlorine or the chloride ligands, right, are going to be able to exchange with all of the water ligands to then form cobalt chloride, which is blue in color, which gives us that blue color that we observe. Okay? So that's pretty much it. Your stability constant is governing what complex gets formed, okay, or which ligand prevails, which ligand wins, okay? So that's really what this is testing us, testing our knowledge of our understanding of that concept of what a stability constant does, okay? So, yes, so this is the answer for part 3. And so let's scroll down and see if there's anything else. I'm just gonna clear this first and then scroll down. And that's it, guys. We are at the end of the June 2016 past paper marathon. I hope that you found this all very useful. And if you have any questions or any comments, definitely drop your comments below and email me as needed. I'll be happy to help you to clarify anything further, okay?